In this slidecast, we'll talk about implementing a stack. A stack is similar to a vector. The standard library defines a stack as a template class that takes any of the sequential containers, either vector, list, or deck, which we'll discuss in Chapter 6, as a template parameter. So we present two implementations in this section, a standard template container and a special purpose single linked list. Here are some UML diagrams that illustrate an implementation of a stack. First, we have a class that's a stack of characters. It has the methods push, top, and pop. And this class has a container that's a vector of characters. And that's going to be the underlying data representation to implement the stack. And here are the fields associated with a vector. We have a capacity, we have the number of items currently in the vector, and then a pointer to an array of items. And it has methods push back, back, and also pop back. This file is the stack.tc file. It's listed on pages 326 and 327 of your text, and I encourage you to go look and study this in detail. This may be too small for you to review carefully. Now, this is the implementation of the functions described in stack.h. And the mechanism we use here is we don't put it in a CPP file. The author puts it in a stack.tc file, which is a file that's included in the .h file in the original stack definition. And the reason for this is that the implementation refers to this type parameter of the template class stack. Remember, in the template class we have an item type, which is sort of a template parameter that is bound to a specific type, such as integers, characters, etc., when we actually declare a stack in our programs. So the compiler needs everything that's normally in the H file and the .cpp file for a template class, so that when someone declares a stack of integers, it can take all of these methods and replace the specific type, for instance, int, for all occurrences of item type that are in these implementations. So go ahead and look through this and see how the template parameters are used and how we have some template functions defined here. And this implementation is similar to the implementation in the standard library. All sequential containers have functions empty, size, back, pushback, and popback. And we take some of these functions and they can be equivalent to the corresponding stack operations of top, push, and pop. So we could use any of these containers as our underlying data representation in an implementation of a stack. The stack class uses the delegation pattern we saw in Chapter 4. It makes functions in the underlying container class do its work for it. We might also call this an adapter class because it adapts the functions available in another class to the interface its clients expect by giving different names to essentially the same operations. So for example, if a vector is used as the container object, then stack push method corresponds to the vector's pushback, and stack top corresponds to vector's back. So in some sense, this is just a renaming, but we rename it to, the method that corresponds exactly to how our abstract data type stack in this case is defined. To implement the stack using a vector object as a container, we change the definition of the data member container in the private part of the class definition. So here we'll define a private data member whose name is container. Its type is a vector of item types. Or we could use a deck, is another container type that we'll learn about in a future chapter. Now, the member function implementations in the preceding listing should be included after the class definition, but before the end of the namespace. So the template member function implementations must be included with the class definitions. So if we look in our stack.h header file, we'll see after the class definitions, but before we end the namespace, we include the stack.tc file. The next slide shows an alternative that replaces each function declaration in the file stack.h with its actual definition. So here we have our stack.h file. It includes vector. We have our own namespace and a template class stack. Then we have, here's some public member functions, and this just includes the actual implementation of the member functions right in the header file. We can also implement a stack using a linked list of nodes. So here's our stack, an instance of a stack. It has a variable top of stack that points to the head of the list. We'll have our regular stack operations, and now the underlying implementation, this is a stack of characters, and it's implemented as a single linked list. So the file linked stack defines a stack class that contains a collection of node objects, and this inner class node has the data fields item type and node star, pointer to a node. So to use this implementation, we replace the statements at the end of stack.h with the following. We include node, then we can have the top of stack simply be a node pointer, and then we can include linked stack.tc, which is an implementation of the stack functions using nodes. Now the pointer variable top of stack points to the last element placed on the stack, so it's easy to insert and remove from the head of a linked list, so the top of the stack points to the node at the head of the list. Now push inserts a node at the head of the list, so this statement top of stack is set equal to a new node, where we pass top of stack also as the second parameter, so that the node that's created now points to the current top of stack. So this is a statement that inserts a new item on the top of the stack. And top of the stack next references the old top of the stack. Now when the stack is empty, top of stack is null, and the attribute next for the first object pushed onto the stack will be null. Top returns the top of the stack data. Empty tests for the value of top of stack equal to no. And pop resets the top of the stack to the value stored in the next field of the list head, and then deletes the old top of the stack. So here's the implementation of linked stack.tc. You should go study this in your book, and here in blue are the code that manipulates the top of the stack using this node list of nodes. The implementation we just looked at is similar to the implementation provided by the C++ standard library. By delegating operations to an underlying sequential container, we avoid having to implement these operations ourselves. And by using push back, pop back, and back, we're assured of order 1 performance, since the C++ standard requires that these sequential containers provide these operations in amortized constant time. Now, using standard containers has a space penalty. To achieve this amortized constant performance, pushback and so forth, vector and dec allocate additional space. So vector will allocate an array twice the size of the current size, and dec also allocates additional space. Now the standard list class is a double linked list, so each node has pointers to both the next and a previous. And stack doesn't need this kind of flexibility, so there is some extra space overhead by using these standard containers. And in some instance, that might be why someone might implement their own stack class so that they can optimize for some of these space. Using our own link structure has an advantage of using exactly as much storage as is needed for the stack. However, you need to allocate the storage for the links. Now, because all insertions and deletions are at one end, the flexibility provided by a linked structure isn't utilized. All stack operations using a linked data structure are order 1. And that brings us to the end of this slidecast.